So, today we are going to look at Josephson junctions, which is at the heart of any circuits made out of superconducting materials. So, the superconducting circuits. This is a very nice discussion on the superconducting properties or the quantum coherence properties of superconductors. So, what happens when two superconductors are placed in close proximity to each other, which could be separated by an insulating junction or a tunnel junction, as it said. So, we are going to discuss what are called as the Josephson So, two regions of superconductors, they are placed in close proximity, as I said, and the quantum mechanical phase of one of them is say phi 1 and the right one is called as phi 2. So, we have two superconducting material, let us call them as S 1 and S 2. This has a condensate wave function characterized by a phase phi 1 and this has a condensate phase phi 2, the phase of the condensate wave function, and they are placed in closed proximity, and this area, the one that is in between S 1 and S 2 is occupied by tunnel junction or an insulating barrier, which we will see. And so, in a normal material, this would not have matter because there is no phase relationship between the two materials that you place in the close proximity. However, in the for a superconductor, or rather for two superconductors, when you place them in this kind of a scenario, then current flows through the system, even through the tunnel junction that lies in between. We will draw the tunnel junction with a shaded or a hatched line. So, a current actually flows through this, and this is called as the Josephson current, and this junction is called as the Josephson junction. And as I said, that just the way the transistors are important to semiconductor electronics, these Josephson junctions lie at the heart of these superconductor based electronics. So, basically strictly speaking, the resistance-less currents that we have said, the current that flows, which is a Josephson current, it is resistance-less, and it is a manifestation of the DC Josephson effect. While there is another situation in which the current actually oscillates with very high frequency, and that is known as the AC Josephson effect. So, this Josephson junctions they are or rather these let us talk about the effects now, which is basically the flowing of the resistance-less current. So, there is a DC Josephson junction, Josephson effect, and there is a AC Josephson effect, and we are going to see what they are in just a while from now. All right. So, any weak coupling between two regions of superconductors, which could be a tiny constriction, which is also known as a microbridge, or there are even point contacts between two superconducting specimens, they also constitute the Josephson junctions. So, let us draw some pictures of these junctions. So, let us so one is you have I am of course drawing it much larger than scale. So, these insulating or the which is called as a tunnel junction. So, this is called as tunnel junction. And these are superconducting just the way we have drawn it, It's just that we have enlarged the view, or there could be so these are the superconducting. So, let us just and then one can have S NS, where N is a normal metal junction. So, these are called as the proximity junctions. Third, there could be a micro constriction. So, this so this is S1 and S2, and this micro constriction could actually be made of the same material as S1 or S2, and all three could be same, but just that fact there is a constriction there, the number of modes carrying current will definitely be affected by this, and this is called as the constriction, or what are called as the micro bridge. And these kind of materials are quite important in the sense that in the superconducting technology, because they are made by a variety of techniques, electron beam lithography being one of them, and one can actually make such junctions and study the properties of material, that is the transport, the charge transport, or rather the current in these junctions, or other properties such as the sensing applications, or them as switching devices, etc., that also can be done. And fourth, so this point contact. So, this is a superconductor and there is another superconductor, and one is connected to the other by just a point contact. So, these are point contact junction. Okay. So, these are micro bridge junction and so on. So, these are some of the examples of Josephson junctions, which so mainly we are going to talk about the one that is shown in serial number 1. However, the discussion is not restricted to one, it could actually be extended to all these other 3 junctions that we have shown here. One important thing about this Josephson junction is that it has usually much lower critical current that is that is there than other just the superconductors. So, critical current is a current beyond which resistance starts appearing, or the voltage starts developing into the sample. So, I will show a typical current voltage characteristic curve of a Josephson junction, and you will see that this is that point so there is a we call it IC, or the critical current, and so basically the Josephson junctions small critical currents IC. IC is characterized by when the system starts developing resistance. So, that is the limit of IC, or rather IC is defined as the current that that flows through the junction in a resistanceless condition. So, developing a resistance is same as saying that it is developing voltage. So, we will say resistance slash voltage. So, these have much smaller IC as compared to the bulk superconductors. And as we have said that they are very important to the superconducting electronics, and they can be used in a variety of situations. So, applications it could be sensors, variable inductors, switching devices, oscillators, amplifiers, and so on. So, there are very large number of applications of these Josephson junctions, and as I said that they are actually central to all the superconducting electronics that one thinks about, and the most important application is in the form of squids, which are called as the superconducting quantum interference devices. So, let us just call it a squid. Superconducting quantum. So, well, quantum interference devices, and we are going to take this up for discussion next after we are done with the Josephson junctions. So, let me just point out that. So, this is S, then QU, and then I, and then D. So, that makes it a squid. So, let us see that what are the predictions of these Josephson effect, or rather so what are the key equations and key sort of predictions and concepts that are involved in this Josephson effect. So, Josephson predictions were one, your current is actually is equal to sine delta phi, where delta phi is equal to the phase. So, this is equal to the change in phase. So, we will write it as phi 1 minus phi 2. So, we have a situation like this. So, this is the tunnel junction or the insulating barrier that lies in between, and this is typically of the order of 10 to 20 angstrom, and this is a superconductor 1 and the superconductor 2. And so, this is usually alumina or the aluminum oxide, which is a well known insulator. And the importance of this is that this is exactly made, or it is possible to make them in the form of a thin layer, and which is insulating. So, it is usually alumina is used, and so this is phi 1 minus phi 2, where phi 1 is equal to phase of the condensate wave function of S1, and similarly phi 2 is the same for S2, okay, or of S2. So, anyway, so this is your just to put things in perspective, that we have the condensate wave function, which is represented by an amplitude part and there is a phase part. So, this is in general a complex quantity and the condensate wave function has this form and we are precisely talking about this phi. So, in at two places in a superconductor, the phase of the wave function is constant and when you put them in close proximity which is separated by 10 to 20 angstrom of an insulating barrier which is known as a tunnel junction, then the current that flows into through this junction is actually a function of these the change in the phases of these two condensate wave functions. So, there is a relationship between the current and the change in phase or rather difference in phase of these condensate wave functions for the superconductor 1 and superconductor 2. Alright. So, this is equation number 1 and there is equation number 2 which talks about the derivative time derivative of the phase. This is equal to a 2 EV over H cross, where V is the voltage that drives the junction and it could be a DC voltage or it could be an AC voltage. So, we simply leave it at that. So, there is a plus and a minus. So, there is a voltage that drives the junction and the voltage is actually related to the derivative time derivative of the phase difference between the superconducting wave function or the condensates, the phases of the condensate. So, V is voltage if we have voltage constant. So, situation 1 we will call it. So, we will talk about the AC Josephson effect first. Consider a constant or a DC voltage driving the junction. So, which means that V equal to constant and if V is equal to constant, then your delta phi is equal to so V equal to constant. So, that means your delta phi is 2 E V T by H cross. So, that can be put back into 1. So, putting it in 1, we have a current which depends upon time and it is I c sine of 2 E V T over H cross. So, you see the current is fluctuating between plus I c and minus I c with the frequency that is given by this 2 V E V T by 2 E V by H cross. So, that is the frequency and that could be pretty large depending upon the value of V that you are driving the junction with. So, this is called as DC or rather this is called as AC Josephson effect, where the current fluctuates between plus I c and minus I c. Whereas, I told that I c is the critical current which is defined for a given junction. Let us now talk about the DC Josephson effect. Okay. So, what happens is that it is not always possible to keep the voltage across the junction constant. a better option is actually to keep the current constant. So, if we have a current that is constant, so I t is equal to some I, which is equal to constant, and that current should actually be less than I c, as we know that this current is less than the critical current. And in that case, this is, so your delta phi is equal to constant, as we see from equation 2. So, if we have the current to be constant, then delta phi has to be constant. If delta phi has to be constant, then the second equation gives that V has to be equal to 0, which means that the bias voltage is equal to 0. So, if that is the case, so this is equal to a sine inverse I by I c. So, which means that the phases of the condensate wave functions denoting the two superconductors, they remain constant at all times, and the difference between the phases is given by the sine inverse of this I over I c, where of course your I c is greater than I. And also, as we understand that from 2, so V is equal to 0 because of the fact that d delta phi delta t equal to 0. So, this is known as DC Josephson effect. Now, this Josephson effect can be very nicely understood from the flux quantization. So, just to remind you that what is flux quantization or why does it come? In a superconductor, if we put it in a magnetic field, then the information about the magnetic field actually enters through the phase of the condensate wave function. So, in addition to an intrinsic phase, it picks up another phase which goes as A dot dl, where A is the vector potential, is the line integral of the vector potential, which using Stokes' law can be written as B dot ds, where B is the magnetic field, external magnetic field, and B dot ds is nothing but the flux. So, the phase of the wave functions get modified by the flux that is threading a superconductor. So, we are talking about a multiply connected superconductor. So, that means that there is a superconductor with a single hole that is there. So, if there is a magnetic field that is threading, so the flux that goes through this is equal to B dot A, where A is the area of this hole here. Now, since the wave function has to be single valued if we make a turn of 2 pi, so which means that the phase here should be same as if you make a turn off by an angle 2 pi, you will still get the same phase. Because of this, the flux that this superconducting specimen or this multiply connected superconductor that can thread can no longer be anything. It could just be multiples of a quantum of flux, which has a value which we have said a number of times, which is very close to 2 into 10 to the power minus 15 Weber meter square. There is a small factor, I mean there is a small number slightly greater than 2, but we are just taking it as 2. Now, you understand that this is the whole idea of interest in this Josephson junctions, and the squids that we will see will share it more elaborately, but understanding that such small magnetic fields can be actually detected. And in fact, the magnetic field associated with human heart is of the order of 10 to the power minus 10 Tesla, whereas the magnetic field associated with brain is 10 to the power minus 12 to 13 or even lesser than that Tesla, which is of the order of picotesla and even smaller than that. Now, what happens is that if there is increased brain activity such as a stroke or things such as that, magnetoencephalography is which is in short is called as MEG, which uses the principles of squids, can actually detect such small changes in the magnetic field, and no other instrument can actually detect such small magnetic field. We will put things in perspective later, where we show that where we are trying to determine magnetic fields which are much smaller than the Earth's magnetic field. So, we can understand this Josephson effect from the perspective of this flux quantization. So, let us So, in order to do that, we will have to take a superconducting ring, because we want a hole which the magnetic field can thread. So, and we will also have a Josephson junction, which means we have a insulating barrier. So, we will take a thick ring. I will tell you the reason for taking a thick ring. So, this is the thick ring. So, there is a hole in between and there is a superconducting material, and we take this region as the tunnel junction or the insulating barrier that we have. So, we have a superconductor on the left of the tunnel junction, and we also have a superconductor on the right of a tunnel junction, which are of course connected. Now, let us draw for our convenience that is going to be immediately clear, that we will draw a contour which is well inside the superconducting specimen. Let us call that contour as C, and we can give a direction to this. It could be the contour. I mean, when we take the line integral about the contour, we can follow this path, and let's denote these points as A and B, and so this is same as A and this is same as B inside the hole. And so, we have this setup which is a Josephson junction, and we are going to use the flux quantization. And it is important to understand that the self inductance effects are small. So, self inductance of the loop itself does not interfere into our considerations in a dominant way. So, what we mean by this is the following. So, which means that LIC is much smaller than phi naught, okay, where phi naught equal to h over 2e, and the value you know, it is 2 into 10 to the power minus 15 Weber meter square. Okay. So, the self inductance of the loop multiplied by the critical current that flows, which is a resistance-less current that flows through the junction, is much smaller than the phi naught, which is the quantum of flux, which has a value which we know. And the contour is placed deep inside, such that the distance from the inner circumference let us call that d, is much greater than lambda, which is the penetration depth, London penetration depth. Now, if all these things are correct, then what happens is that the magnetic field is of course 0 in the specimen, and we can write down from London's current equation, so your J r, this is equal to, it is a gradient of phi, where phi is of course the phase, minus 2 e by h cross a r. This you can see your notes. So, this is called as a London equation. For J r equal to 0, which is the current density in the superconducting specimen equal to 0, this is how the Meissner effect is actually derived. So, this is equal to 0, that gives that this grad phi is equal to 2 E A r by h cross, and if we do an integration, doing an integral along the contour C, we have a grad phi dot dl. This is equal to 2 e over h cross a dot dl, which is equal to 2 e over h cross b dot ds, and this is equal to 2 e over h cross phi. That is the flux that threads the ring, superconducting ring, because of the external magnetic field B. So, this is equal to 2 e by h into 2 pi, this h cross can be written as h over 2 pi, and then phi, and then 2 e over h is nothing but 1 over phi 0. So, this becomes 2 pi phi over phi 0, where phi 0 is the flux quantum. So, that tells you that delta phi, that is the value of the change in the phase going from A to B along the contour C. So, this is equal to nothing but it is a multiple of phi over phi 0. Now, this is an important equation that tells that the superconducting phases will be different by not an arbitrary quantity, but by a quantity that is a multiple of phi naught. So, phi over phi naught is actually a number, and then of course, that is be multiplied by 2 pi. And so, there is a relationship between the external flux and the change in the wave function between the points A and B. So, we can write going from A to B. So, if we take this equation and take a derivative of this equation, then we have to take a derivative, because phi naught is a constant, we can take a derivative of phi. So, d phi dt will be nothing but the induced EMF, and we can write it down again as 2 e over h cross v as a function of t, and this is nothing but Josephson's second equation, which we have written by 2. Where v of t is nothing but the EMF developed or the voltage drop across the junction between A and B. So, what is the current versus voltage characteristic curve for a Josephson junction? Okay. So, if we plot V this way and I this way, then of course, your at the middle. So, we have so this is your V voltage in volts, and this is your current I. So, this is the superconducting current. So, let us just shade it with a different color. So, this is the Josephson current or the superconducting current. Current, and so these are whereas this and as well this are due to normal electron tunneling. And this point, this is called as the critical current. So, basically when the voltage starts developing or the junction starts developing resistance is what defines as the critical current. Okay. So, let us do a small calculation of a junction, a Josephson junction, and see the current characteristics and so on. See, just rotating our picture by a little bit such that you get a full 3-dimensional view. So, these are that is the insulating barrier, which is, and there is this superconductor S1 and S2, and so this is your suppose this is your x axis and this is your z axis and this is your y axis. Then we have there is a current, that is there is an ammeter and this is been biased. So, this has say a width of 2a and so on. So, this is your the picture of a junction. What is important for us is that we have a junction like this from minus a to plus a, such that the width is basically 2a, and there is an incident energy is equal to epsilon, and this has the potential, barrier potential is equal to V 0, and this is of course your V as a function of x and this is your x. And so, we are going to solve a single particle Schrodinger equation in order to see or rather calculate the current. It is important for you to understand that the current is continuous across the junction. So, there is a current that is flowing and the current cannot just disappear coming at the at the border of the superconducting and normal. So, the current will be continuous, and for the current to be continuous we can, so it is entering into a regime which is classically forbidden. So, this it will undergo a decay and we will have to calculate that or rather take into consideration by writing down the Schrodinger equation and taking into account the boundary condition, proper boundary condition at the edges. So, the wave functions at the superconducting electrodes it's equal to psi r t, which is equal to a psi naught r, which is the amplitude, and the phase which is we have discussed that it goes as the V t by h cross, where theta of t or phi of t, rather we were writing it as phi. So, phi of t is equal to V t over h cross and so on. So, it is a DC voltage that is applied. So, we will have a Josephson current there, which is otherwise classically forbidden. So, we can write down the single particle Schrodinger equation as so, this is equal to I h cross del del t of a psi r t, that is a time dependent Schrodinger equation. It is a 1 over 2 m star, where m star is the effective mass minus I h cross del, that is the mechanical momentum, and then there is a canonical momentum which can be obtained in presence of a magnetic field like this, and this psi. So, this the first term is the minus, so it is basically the p square over 2 m. Now, p has become minus I h cross del minus E a, and there is an electromagnetic field. So, we have a E star phi, which is characterized by a scalar potential phi and a vector potential A. So, this is R t psi of R t, and we will finally write for a barrier. So, this is V of x psi of R t. Okay. And in this particular case, of course, V of x is equal to constant. So, in absence of the EM field, just switching it off now and writing writing down the time independent equation. One gets minus h square by 2 m star. So, m star and E star are included because they are effective masses and effective charge of the particles. So, this is and d 2 psi, I am writing it in, of course, in now in one dimension. So, this is equal to d 2 psi dx 2. This is equal to epsilon 0 minus V 0 and psi. Now, this is only a function of x, we are writing in one dimension. So, we write 1 d. All right. So, now this you see a negative constant, because epsilon 0 and V 0, the epsilon 0 is the energy of the incident particle. So, this is a negative constant. So, you know what happens when you have a negative thing that appears here, you have a decaying solution. So, we have a solution which is either you can write it in terms of exponential, but in a constrained geometry we usually write it in terms of cosine hyperbolic and sine hyperbolic. So, this is C 1 cosine hyperbolic x over xi plus a C 2 sine hyperbolic x over xi. Just to remind you that if you have a second order differential equation, if the C 1 cosine hyperbolic x over xi, I will write what xi is a solution, and C 2 sine hyperbolic or rather just sine hyperbolic x over xi is a solution, then a superposition of that with constants, arbitrary constants, such that constrained to the fact that C 1 mod square plus C 2 mod square is equal to 1 is also a solution, where xi is nothing but the momentum vector, which is written as h square by 2 m star v naught minus E naught. All right. So, then of course, the current is given by, of course, it has a longer expression that you are familiar with. It is h cross over 2 m I psi star d psi dx minus psi d psi star dx and so on. That can be written in a compact form as 2 e star over m star and a real part of psi star h cross by I, and write a grad psi, but it means a d psi dx. So, this if you compute it, it becomes equal to m star psi imaginary part of C 1 star C 2. So, that tells you that at the boundaries applying boundary conditions, so psi of minus a, it's basically equal to. So, what happens is that you have in this particular geometry which we have drawn in the last slide. So, we have a minus a to plus a and a barrier is V 0, there is this epsilon 0. So, here what happens is that you have the wave function that decays, and then of course, it grows in order to connect smoothly to the other region. So, this is a minus a and this is a plus a. So, this is so that tells you that this is equal to a root over n 1, where n 1 is the superfluid density of superconductor 1. So, this is a S 1 and S 2. So, which is characterized by a root over n 1 exponential I phi 1, and this is root over n 2 and exponential I phi 2 and so on. So, this is equal to exponential I phi 1 and psi at plus a, it is equal to root over n 2 exponential phi 2. So, we are in a general sense, we are talking about two different superfluid densities, where these n 1 and n 2 are actually mod psi 0 square, which is the amplitude square. So, if you apply these boundary conditions to these solutions that are written here, so these are the solutions of the Schrodinger equation. So, if you put them there, then you can evaluate the coefficients, which goes as n 1 exponential I phi 1 plus n 2 exponential I phi 2 divided by a 2 cosine hyperbolic a over xi, and for C 2 one has a n 2 exponential I phi 2 sorry n 1. So, it is n 1 exponential I phi 1 minus, what did I write? Why did I write 2? It is a n 2. It is n 2 exponential I phi 2 divided by 2 sine hyperbolic a over xi. So, these are we have now calculated this. So, your J s which now can be put there. So, J s becomes nothing but a J c and a sine of phi 1 minus phi 2. So, this is equal to a J c sine delta phi, and where J c is equal to E h cross root over n 1 n 2 divided by m xi sine hyperbolic 2 a over xi. So, we have achieved quite a bit. You see that we have written down predictions of the Josephson current, that the current would be oscillating in this particular fashion, or we wrote it of course for the current, and here we are derived it for the current density, but of course, if we multiply it by the area it remains the same. So, there is a sinusoidal variation and the argument of the sine function that involves the change or the difference in phase between the two superconductors. So, now if we want to go back to our electromagnetic field, so then it becomes so your delta phi now, in addition to the phi 1 minus phi 2, it picks up the same phase that we talked about between 1 and 2. So, these are these minus a and plus a and then this dl. So, the rate of change of phase is a d delta phi delta t. This is equal to a del phi 1 del t minus a del phi 2 del t and minus 2 pi over phi 0 del t of 1 to 2 a r t dot dl. So, in general I mean this is just a convention, but you will find different conventions at different places in literature. A Josephson junction is represented by a symbol like this. It is like two inverted triangles that are connected here, and so there is a V. So, so this basically has I equal to I c sine delta phi and a V equal to phi 0 by 2 pi d delta phi dt. So, these are the equation. So, one has the work done by such a junction. So, it is W j, there is a Josephson junction, it is in a time 0 to t 0 which can be chosen. So, this is equal to 0 to t 0 I c sine delta phi prime which is a function of t and a phi 0 over 2 pi. Now, it is a v which is a d delta phi prime dt and dt. So, on it is just the phi prime is just the dummy variable that we have taken here, and if we integrate it, it is a simple integration to perform. It is equal to 2 pi and so it is from 0 to some delta phi and sine of delta phi prime d delta phi prime. So, this is basically the integral that comes out, and this is equal to I 0 phi 0 I c over 2 pi and a 1 minus cosine delta phi. So, that is the work done or that is the energy stored in the junction. So, it can be actually used to store the energy, and a simple plot of the the current and the work done can be shown as like this. So, there is this the current fluctuates like or rather oscillates like this. So, this is current I s or I over I c and let us draw it with a different color. So, this is so this is your W j minus W j 0. This is just a normalizing factor that is being used, phi 0 I c over 2 pi, that variation is shown with delta phi. So, this is a function of delta phi. And so, there is a sinusoidal variation that is that one can see it here. And so, basically this is a brief description of the Josephson effect that one needs to know, and the reason that we have introduced is that we are going to do squids and the some applications in very brief, and in order to understand squids, both the DC and the RF squids, one needs to know and learn Josephson junctions.